Alright, so in this video I'm going to cover the topic of time and length, dilation and contraction. So let's dive in. So the first important point to understand, if we're going to understand anything about time and length, dilation or contraction, is that the speed of light is always equal to c. So the speed of light is always equal to c, it's always constant, no matter if the source it comes off of is moving, not moving, whatever, it's always c. It's going to be very important soon, as we're going to see in this first example I've drawn right here. So this picture shows two people, person A and person B. Person A is in a train car going to the left as shown by the arrow, and person B is somewhere in the distance just observing what's happening. And what is going to happen is that as person A rolls along past person B, as soon as person A is directly in front of person B, person A is going to flip a switch that's going to turn light sources 1 and 2 on the left and the right, as you can see. He's going to use a light switch to turn both of them on at the exact same time. Now the key here is that light sources 1 and 2 are the exact same distance from person A. So logically we think that as soon as person A turns on light sources 1 and 2 with his switch, that the light from both sources would hit person A at the exact same time. Because if they're both going the same speed, c, and they're both the same distance from him, even though he's moving, they should hit him at the same time. And that is actually exactly what happens from person A's perspective, that is. When person A turns on the light switch and sees the lights come towards him, because they're always the same distance from him and he's moving with the lights both reach him at the same exact time. But person B is the interesting part, and we're going to discuss the most. Person B sees a slightly different, actually very different outcome from this experiment than person A does. So as person A passes person B and turns on both the lights, person A rolls past person B, and person B sees this image right here of person A. Because person A was moving to the left towards light source 1 that we saw over here, that means that the distance between him and the light that was emitted from light source 1 from person B's perspective has a shorter distance to go because person A was moving towards light source 1. And you can see I've drawn these lines right here to show that effect. This is exactly what person B sees. He sees the light from light source 1 on the left hitting person A before the light on the right hits person A. How can that be? That's pretty crazy, right? But that's what he sees. So what can we learn from this experiment here? What do we discover? The first thing we discover is that because person A and person B didn't see this exact same thing happen at the same time, we learned that simultaneity is not absolute. That two people observing the same event can see things happen at different times. Person B saw a time contraction relative to person A because the light from the left, I'll show it again, hit person A sooner for person B than for person A, from person B's perspective. Alright, with that example out of the way, let's go to a more quantitative example to really understand this concept. So another scenario here, we've got a spaceship right there. Person A is inside of it doing an experiment again. Person A loves doing experiments apparently. And person B is on Earth observing person A and what person A is doing. Person B loves to observe person A, apparently. So let's zoom in on person A in the spaceship. So person A's experiment is he's got another switch, and that switch will turn on a light bulb right there, shoot light up to a mirror, and then back down to a black box, and that black box records the time it takes from the moment the light switch is flipped to turn on the light bulb until the light comes to hit the black box. So that time between light switch, mirror, and then black box. It records that time interval. So when person A does the experiment, they see exactly this picture right here. They turn the light on, light goes out from the light bulb, hits the mirror, reflects, comes back to the black box, and that's how long it takes. And because the speed of light is always c, we can discover how much time it takes that light to hit the black box. We can define that in terms of d, the distance between the mirror and the black box. Because if the speed of light is always constant, all that changes is the distance and the time. Person B, however, again sees a little different scenario play out. Because the spaceship is moving relative to person B also sees the light travel a horizontal distance because the spaceship was traveling horizontally. And now I've diagrammed that right there in red. So I'm going to call the distance that person B sees the light travel to be s. And s is just the horizontal distance and the vertical distance summed together in a vector format to make a diagonal line that you see on the board right here. And if we define the distance that the spaceship traveled entirely while the light was going to the mirror and back, if we call that L, we can say that the distance it takes the light to go from the black bulb to the black box is L over 2. And we can make these nice triangles right here. With these triangles, we can define S to equal the square root of d squared plus L over 2 squared, just using Pythagorean theorem because these are right triangles. All right. So from this triangle, we can see that S must be bigger than D because S is the hypotenuse, and the hypotenuse is always the longest side of a triangle. Therefore, person B relative to person A, the light took longer to get to the black box for person B than person A because it traveled a farther distance at the same velocity. So therefore, it must have taken a longer time to get there. This brings us to two important symbols we use for problems involving time dilation, time contraction. So the first one on top is delta t naught, and we call that proper time. And this is the time measured by an observer that is moving with the event. So in this case of the spaceship, person A would be measuring proper time because they're moving with the event. Whereas person B would, their time measured would just be delta t with no naught symbol. And delta t is always going to be the time measured by the observer who is not moving with the event. Again, he was stationary the whole time that the spaceship was rolling by him, so therefore he must have been measuring delta t, not delta t naught. Not delta t naught. not measuring proper time, just delta t. So using the equation for velocity equals delta x over delta t, we can plug in c for velocity, since that's always the velocity of light. We can rearrange to solve for time. We can define proper time as the distance. Well, the distance would be 2d because the light for person A goes 2d to get to the mirror and then the black box. So this is the equation for proper time right here, 2d over c. Whereas for person B, so the light travel s, 2s actually. So their equation is 2s over c. If we plug in d, s, and l, all from this triangle and this Pythagorean theorem equation, into this equation right here, these two equations as a system of equations, solve for delta t, do a lot of math I'm not going to show because it's pretty advanced. It's in the book if you want to look at it. But this is the equation you're going to get if you do that. You're going to get the equation for relative time. Delta t equals proper time over the square root of 1 minus v squared over c squared. This equation has been tested many times by many experiments over many years, and it's shown to be true. Now this equation will give you relative time for an observer standing still, observing an event. Alternatively, we often define this equation as delta t equals gamma times proper time, where gamma is simply 1 over the square root of 1 minus v squared over c squared. So same equation right here, as you can see, just plugging in gamma gives us the exact same equation. One note is that v in this equation, v is the velocity of the event relative to the observer measuring delta t. So let's practice a little bit with this equation. So let's say there's a short-lived particle who's going 0.95 the speed of light, and it measured its own lifespan to be 5 seconds. Short life, but a good one, I guess, hopefully. So the question is, what would a stationary observer measure that particle's lifespan to be? So the only kind of hard part about these problems is figuring out which observer is measuring proper time and which observer is measuring not proper time, just delta t. In this problem, I'll go give the answer. Hope you thought about it, I guess, a little bit. The particle, because it's moving and measuring its own lifespan, which is the event, the particle measures proper time, and the person stationary is measuring delta t. So, knowing that, we can plug in 5 seconds for proper time into the equation. Proper time's on top, 5 seconds on top. And we can plug in 0.95c for v in the equation, and just plugging the numbers and solving it gives us the fact that the observer, who is stationary, saw the particle's lifespan as actually being 16.01 seconds as opposed to 5 seconds. And this shows a pattern here, if you can see it, that the faster something's going, the more dilation an observer is going to see for it, because that bottom numerator, or the denominator, changes in that fashion as numbers get bigger. Alright, we're going to take a look at one more equation and 2 more variables, and this will deal with length contraction and length dilation. So if we plug in the equation for relative time into these equations over here for c equals delta x over delta t, we can solve for this equation right here, which is the equation for relative length. And we find that it is relative length equals proper length times the square root of 1 minus v squared over c squared. So pretty similar to the equation for proper time, only that instead of multiplying by gamma, we're dividing by gamma. One more thing that's different, that can be a little confusing for people, is that the rules for determining which one is proper length, which one is relative length, are pretty much the exact opposite of the rules for telling apart proper time and relative time. So, proper length is the length measured by the observer who is not moving with the event. Remember before, proper time was measured by the observer who was moving with the event. So like I said, it's kind of the exact opposite, but as long as you know one of them, it's pretty easy to keep straight. Just think the other one's the opposite of the both propers are opposites of each other. So with that definition, relative length must be the length measured by the observer who is moving with the event. So we'll do a quick practice problem with this. So take the particle problem we just did a second ago, and the stationary observer thought that the particle that he was observing went 100,000 meters. So the question is, what distance does the particle think it went? So if you just plug in 100,000 meters for proper length, because the observer here is proper length because he was standing still, we just plug in 100,000 meters, multiply by gamma, and we get 31,000 meters about. So this shows that the faster something is going, the less distance they think they went in the same amount of time. And that will sum up time and length dilation contraction. Thanks for watching.